us start module 2. Okay. So if you remember from the course objectives, one of the most important things that we're going to learn in this course is how to evaluate a processor and a computer system in general. So obviously one of the important things that we need to focus on, and we need to begin with, is the fundamental of the quantitative analysis. We're going to go over the metrics that are important for quantitative analysis of the computer system. And this part is actually coming from the first chapter of the Patterson and Hennessy book, Computer Organization and Design, as well as the first chapter of the Computer Architecture Quantitative Approach, and still some of the slides from Dr. Ronald DeMar from UCF. Some of you might be familiar with some of the topics that I'm going to cover today. From the Intro to Computer Architecture, we're going to have a little bit more depth to it. And I actually, when you read the chapter, it goes all the way to Amdahl's law, and I intentionally don't cover that part now, and I cover that part right before the module that we talk about parallel processors, because that part is actually related to parallel processors, and it's going to be more useful if you get familiar with that right before that section. So if you actually go to the chapter, we're not covering the entire chapter in this module. Some part of that is remained for, I think, module 9, which is actually the last module of the class. All right, so when we talk about quantitative analysis, the most important thing is knowing what the metrics are and what they're used for. So one of the most important metrics for evaluating processors and computer systems in general is throughput. So throughput is, as you can see here, equal to how many outputs we can get in a specific time interval, right? So here we're not talking about how fast the system is. We're just looking at the number of outputs that we can get, right? So this is a very important metric for data centers or some other applications. For example, as I mentioned before, in my lab we work on a project that is for designing a hardware for blockchain applications, and from the beginning, the company that was funding this project told us that they care about throughput. So they don't care about how long it takes to go from input and output. They care about how fast you can get the outputs, right? So you're going to learn a little bit more about it, because now it seems like the same thing, because if you can have a high throughput, you're probably going to get more inputs, outputs, and also if you reduce the execution time, you can get more outputs. But with some examples, you can see the difference of these methods. The next one is the response time. So response time is the time that it takes between when we apply the input until we actually get the output, right? So maybe we can understand it better with an example. Older Apple phones, they didn't have this machine learning chips in it. So they would do anything that was related to machine learning and audio processing, video processing, image processing in a data center, right? This was not actually happening in your cell phone. So whenever you were asking Siri to do something for you, your phone was actually working as an input-output device. The processing wasn't happening there. So where does the processing happen? It's somewhere, some data center, there's actually called cloud, but there's an actual processor somewhere in the data center that is doing the processing, right? But then we have the internet access and everything, so we send the data through to the cloud, then the processing happens, and this data is sent back to us. From the time that we ask Siri to give us an address or something, to the time that we actually receive it, this is response time. But this entire time is not spent on actual audio processing, right? Some time we spend on the network, for example, the network time, as you can see here, we can have the memory time, disk time, and the CPU time, right? So response time is usually longer, and we just care about when we apply the input and we get the output, right? It's important for us as users because we don't really care about what is happening behind the scene. If you're an application developer, you want it to be fast. And you don't care if you have the fastest processor in the world, but it takes forever to reach the processor, your application is going to be slow anyways, right? The next thing which is very important in this class is execution time. It's called CPU time, processor time. This is the actual time we spend on processing data. So we have the input, we don't care about how long it takes for network to deliver that input to the processor. We just care how long it takes for the processor to finish that task. In that example that I mentioned, the audio processing part is what is happening in the CPU, plus some search. And that is what is the CPU time and execution time is. Here in the computer architecture course, we mostly care about that, the processing time, right? There are different courses on network design, and they care about the network time, how long it takes to transfer data in them. So this is very important for ASIC designers. ASIC is application-specific integrated circuit. And also FPGAs, if you're familiar with FPGAs, there are some programmable fabrics that can redesign, reprogram your design. So these are the things that, and also CPU, mobile CPU. So a lot of the research that we do in our lab, in my lab, is focused on execution time. Because we don't do research on network, we do research on computer architecture and the processes. So we actually try to optimize the processing time. Okay, so these are the three important metrics: throughput, response time, execution time. These are all related to speed. We obviously have different metrics like power, energy, reliability. These are the things that we're probably going to see some of them like power and energy later. But we have different design objectives, and it is usually defined by the user and the application. So here, again, in computer architecture course, we probably don't talk about reliability, for example, or radiation hardness. So we used to work on a project that was funded by DARPA and NASA, and they were sending satellites, and what happens there, we have a lot of alpha particles, and they were attacking the transistors. So what would happen was you design a processor, you send it to space, and then because of the radiation, the transistors stop working. It's called hard fault, right? You have soft error and hard error. Hard error is when the transistor is completely ruined, so you can't do processing. Soft error is just when you have a memory and the radiation attacks the memory and it flips the bits. So you have 0, it flips to 1, and so on. So the goal of that project was not performance, was not throughput, execution time. The goal was availability. So they wanted to keep the system available as much as they can. And also reliability. So the design that we had was a FPGA design and on top of that we had a genetic algorithm, and what would happen was when the radiation attacked this computing system that we had, it automatically redesigned itself. We called it evolvable hardware, so this hardware was evolving, but it wasn't completely out of the system. So it was still working, the accuracy was reduced, we had some cases of edge detection, there were satellites for maps and stuff, so we were doing edge detection. You could see that it's getting a little bit worse in terms of accuracy, but you can see that the design starts evolving and gets better. And And that was one project that was just focusing on reliability and availability. These are a little bit more advanced topics. So usually, if you have advanced computer architecture, for example, you go into these topics. In the computer architecture, we just care about speed and probably power. Not even power that much. We usually care about performance and execution time, right? And that's why we focus on these metrics first: throughput, response time, and execution time. Okay, so I just said that there might be some cases that you have a high throughput without increasing the execution time, right? Obviously, you can increase the throughput by increasing the execution, by decreasing the execution time. So if you design a better processor and it takes 1 second to finish a task compared to a processor that needs 10 seconds to finish a task, obviously you have 10 times more throughput. That's one way of doing it, right? But it doesn't have to be like that. So just as a thought experiment for us, how do you think we can increase the throughput without making any improvement in the processor? We have a system that wants to complete a specific task, and we don't want to really improve a CPU. Go ahead.
If you do batch operations rather than doing them one at a time.
Yeah, it's very close. It's a type of parallel processing. Parallelism is one way of doing it, right? So you don't have to have one CPU to finish a task. You can have like 8 CPUs doing that, right? Or you can have multiple cores, right? There was a time, I think it began in early 2000, that processors started having more cores, right? We have Core i5, Core i7, right? So a lot of these designs don't necessarily improve their core, right? Some of them do, but they don't necessarily improve their core, but they just add more cores, right? And they distribute their workload on different cores. That's something that we're gonna learn in this course. When it gets to the, I think, module 9, when we talk about parallel processors, we talk about multi-threading. We talk about these concepts. So parallelism is one way of improving the throughput without improving the processor performance, right? But there can be simple ways too, like this. So this is something like bit-to-bit bandwidth doubling technique. So this is the difference between 64-bit processors and 32-bit processors, right? So this is as simple as transferring more data at a time. You're not touching the processor here, we're just sending more data every time, right? In many real cases, they actually do change the processor because now they can do 64-bit operations, right? We're gonna learn about this. So 64-bit processors, a lot of them in the beginning, they didn't have 64-bit operations. So they couldn't do 64-bit add, for example, right? They just had 32-bit add, but they could add 2 numbers that were both 32 bits, but they just made the data bus 64 bits. And it means that you send enough data to do 2 computations at the same time, right? So this was a simple thing that they did, going from 32 to 64, without necessarily changing the processor, but later they actually changed the processor too. Now, good processors, they actually do 64-bit multiplication, 64-bit addition, and so on, right? So this is bandwidth doubling. Throughput increases because you reduce the data transfer time and your entire systems become faster, and the throughput of the entire system is going to increase, right? So if you look at this design, one of them is a 32-bit processor, the other one is a 64-bit processor. Throughput increases because we have more lines, but the latency, for example, let's say 50 nanosecond is the time that it takes to send the data from memory to processor and vice versa. That is the same thing. You still have the 50 nanosecond, just send more data, right? This is another kind of parallelism. It's called bit level parallelism. So you increase the data loss, right? Any questions so far? All right, the next important metric is performance. So a lot of research papers just focus on performance, right? And the reason is you can increase, this is my opinion, by the way, this is not a fact, right? But you're here to know about my opinion, so if you're not, I'm gonna give you my opinion anyways. So a lot of research just focus on performance because increasing throughput can be mostly an engineering task. So when you go for multiple cores, it does have its own difficulties, but it's a pretty engineering task to deal with. But increasing the speed, the performance of one core is a very research-related task that you have to do. So it needs innovation beyond just having multiple of them on a chip, right? That's my opinion. There are people who disagree with me, mostly the system level guys, because when you have multiple cores, then at the system level you have to manage the workload, and that's what their research is. But most of the computer architecture research is focused on performance improvement. Okay, so what is performance? We want to increase the performance of the processor. We have to decrease its execution time. It's as simple as that. So performance, as you can see here, has an inverse relation to the execution time. If you calculate the execution time and it's 2 seconds, your performance is 0.5, right? And then you can use this simple relation for relative comparison of two processors too. So if you want to know the performance of processor X compared to processor Y, you just get the performance of X over performance of Y, and because there's an inverse relation here, you divide the execution time of Y by execution time of X, right? This is called relative performance measurement. Relative performance measurement is as simple as this. You get the execution time of two processors, you divide them, and you get the relative performance. If you heard the term speed up, this is how you get the speed up. You have you have a base processor, and you have an improved processor, and then you just divide the performances, and you get speed up. And it's a 20% increase. It's as simple as that. And then we have the absolute performance measurement that can be the execution time itself, throughput, and so on. All right, we have a question here. You just try and see if you can solve it. We have a 64-bit A7 processor that needs 30 milliseconds to execute a video compression program. And then we have a 32-bit A6 processor that needs 600 milliseconds to complete the same task. So what is the relative performance of A7 chip compared to A6? A7 needs 30 milliseconds, A6 needs 600 milliseconds. What is the relative performance of A7 compared to A6? It's 20, right? So we have 30 milliseconds. If you want to go based on the equation, performance A7 over performance A6 is equal to execution time X6 over execution time of A7. The execution time for A6 is 600 milliseconds. Divided by 30 milliseconds, we're going to get 20, right? So this is the speed. We don't have speed up here, but the relative performance is 20. And we can say that the processor A7 is 20 times faster than processor A6. Or we can say the execution time of the processor A7 is 20 times smaller than the execution time of the processor A6 for the same video compression task, right? All right, the next thing we need to know is the concept of clock. How many of you guys have heard about clock? So when you want to buy a computer, you can see something in, there's a spec that says a few gigahertz, 3 gigahertz, 4 gigahertz. That's a clock, right? Clock is a signal like this. It oscillates between a high state and a low state. And the highest state is the nominal voltage of your design. So this is circuit level work. Usually in the circuit we have ground and we have VDD. VDD is a nominal voltage. And clock oscillates between VDD and ground. The VDD is the high state, ground is lowest state. So for example, in this case we can have 1.2 volts as VDD, which is the highest state of the clock, and ground is always 0. And then if you really measure, if you have a clock generator on circuit, and if you use oscilloscope to see how it looks like, it does have some, it's never perfect. It looks like this, right? You can see some fluctuations, small fluctuations there. And for that reason, usually when we define a 0 and 1, in digital logic, we say anything more than 1 volt, for example, is 1, and anything less than 0.2 volt is 0. Because we want to give it some space to make those fluctuations. And we don't switch from 0 to 1. This is a clock, right? Some of the things that we have to define here is the concept of edge. So when we go from low state to high state, we call it the rising edge. And then we go from a high state to low state, it's the falling edge. And then we have the clock period, which is the time between 2 edges, 2 rising edge or 2 falling edge, right? Clock period. This is how it is defined. Clock is used to synchronize everything in your design. We talked about the concept of register last time. We have registers in the processors. There are small memories in which you store some data. They're pretty fast, but we can't have many of them because it's very expensive. We can't have millions of them. They're very expensive, but they're really fast. So registers in a processor are updated in one clock. Usually you say at the rising edge of the clock. So when you have the rising edge of each clock, you update the registers, right? Literally when you have system Verilog code, you write always at past edge of clock, do that, do this, right? At the hardware level, you simply clearly say that do this in the positive edge, and you can also say do this in the negative edge. This is called asynchronous design. We can have synchronous design and asynchronous design. The synchronous design always works with the same edge of the clock. Every instruction in the processor starts with a clock. So if you want to execute an instruction, if you want to do add operation, you start with the clock. The clock is responsible for making everything synchronized in a processor. The faster it is, the faster you do the operations. Now, let's wait for the next slide and then I ask that question. For now, let's just talk about the concept. So clock period is equal to clock cycle time. And clock cycle time is the time between 2 edges of the clocks, 2 consecutive edges, right? And usually the clocks have the same duration of high state and the same duration of low state. So usually this duration is similar. We have the same, if the clock period is 1 second, usually we have half a second in high state, half a second in low state, and this is what is called a 50% duty cycle. You don't have to have 50% duty cycle. You can actually create different signals from the clock, but usually for the digital design, the clocks are 50%, they all have 50% duty cycle. Sometimes for analog design or for other application, you can have duty cycles that are not exactly 50%. Even for digital design, you might do it, but it is when you want to create a different clock. So you can actually have multiple types of clocks. You can have a base clock, and from that you can create different clocks for different parts of your circuit. So you have a design and you want to have different speed in your design, so you can generate the clock from the original clock, and then you can tune the duty cycle based on your application. Again, these are the things that I'm mentioning now, just for you guys to have some idea when you hopefully gonna do some system Verilog coding. But when we say do this in positive edge of the clock, you have some idea about the synchronization, right? Any questions so far?
If you have a base clock that's synchronizing everything, and let's say its duty cycle isn't quite 50%, would that matter? If it's the authoritative synchronizing clock, I mean, would you even be able to notice if you have ended up with like a 48% duty cycle?
It's a very good question. It matters if you, for example, are doing something at the negative edge of the clock too. So if part of your system is working at the negative edge of the clock, and if your duty cycle, for example, is not long enough for both cases, you might not be done with that part, and then you activate another part of your design, right? So it matters if you are doing something with the negative edge of the clock. If you always work with the positive edge of the clock, it doesn't.
I have another question. When you were talking about the difference between synchronous design and asynchronous use of the edges, I was a little confused on, like, when you say like a synchronous design, would you mean would you mean the different actions that, would you do them all on one edge, or would you do specific actions on specific edges?
So I have to make it clear a little bit. So asynchronous design is a big thing by itself. So we can't oversimplify it by saying, now just because you're asking the question, I want to clarify this. Because I just mentioned something, but asynchronous design is beyond just working with clocks. So sometimes with clocks, you always do something at the clock. Asynchronous design involves something like handshaking, for example. Is that you don't really work with that, you wait for the other part of the circuit to complete its task. So it's a little bit more complicated than just playing with the edges of the clock. I don't want to go deeper into it because it's a very digital designing kind of topic, but one of the things that we do, for example, when we are designing brain-inspired computer architectures is using asynchronous design. So Loihi is a chip that Intel developed, which they say is the brain, is very similar to brain. It's not commercially available yet, but we do have access to it in our research lab because we have collaboration with them. And that is asynchronous. You know, they call it event-based, it's asynchronous. So it's a little bit beyond that. I don't want to start it because I don't want to confuse you later, but it's an entire topic by itself. There are a lot of papers published in that area. Cool, yeah. Okay. So now we have the clock cycle time. What is the clock frequency? You probably have heard about clock frequency a little bit more because, as I said, when you want to buy a computer, all the specs are in clock frequency. Clock frequency is simply 1 over clock cycle time on 1 over period, and the unit for that is hertz. It is also called clock rate. And clock frequency is the same as clock rate, is 1 divided 1 over clock cycle time. So these are some of the familiar numbers here. I just put it here for you to know. And as a computer scientist and a computer architecture, computer engineer, it's good to know these things. You don't have to go back and check your Google this to find it. It's simple. So when we have 1 gigahertz, it means that the clock period is 1 nanosecond. It means that you're going to have 10 to the 9 clock cycles in 1 second, right? 10 to the 9. So that's the concept of clock frequency. How many clock cycles you're going to have in 1 second. So when we have a clock frequency of 1 gigahertz, it means we have 10 to the 9 clock cycles in 1 second. And clock period is 10 to the negative 9, just 1 nanosecond. We have 100 megahertz embedded systems. Usually you see 100, 200, 500 megahertz clock frequency. When you go to data centers, you go to 4, 5, 6, 7 gigahertz. So 100 megahertz is the clock frequency 100 megahertz clock rate has a clock period of 10 nanoseconds, for example. These are some of the metrics that I just put here. We usually, these days, we work with nanoseconds and picoseconds. We don't really work with microseconds too slow. These days, so like your microseconds get into megahertz and kilohertz. These are not for computer systems. For communication systems, you see a lot of those frequencies, but it's not usually for computer systems. For computer systems, we have a few hundreds of megahertz and some gigahertz. Okay, so now with this information about the clock and the fact that clock is synchronizing everything, we're hoping to finish every task in one clock cycle and so on. So let's talk about some strategies to increase the performance, decrease the execution time, right? So if we just want to talk about clock, how do you think we can improve the performance by modifying the clock? If you want to have, go ahead.
Increase the clock rate.
If we increase the clock rate, we're going to have higher execution time. So why can't we? It's a difficult question. You might not have a clear idea about it, but let's just, for the fun of it, let's think about it. Why can't we just increase the frequency like crazy? Why don't we go to 20 gigahertz, 50 gigahertz, 100 gigahertz? Why not? What is limiting us? Any ideas? Don't be shy.
Constrained by the speed of the hardware itself.
It's a very good answer, actually. Speed of the hardware, and by which we mean that it takes some time for us to complete a task, right? We have transistors. It takes some time to finish, for example, one addition. When you design, as I said, in assembly language, we break everything down to smaller instructions, like add, subtraction, shift, very simple instructions. It takes some time to finish those instructions. If we increase the clock frequency to 20 gigahertz, to 10 gigahertz, it means that your task should be finished in 100 picoseconds. Otherwise, you mess up with your system. You keep sending commands and you don't wait for it to finish, right? That's what it means. If I don't have a fast enough adder, if I clock it at 10 gigahertz, I don't give it enough time to give me the result of the add, right? So that's one way if you look at it from the computing system. Generating clock itself is not that easy either. So that's not the research that we're going to do, some material science kind of research. But right now we can generate clocks close to 100 or terahertz even. But the limiting factor is the computing circuit. It takes some time to do the task, no matter how small it is. Or no matter how small is one addition, it takes some time. And when we talk about 10 gigahertz, 20 gigahertz, these are pretty fast. Even a circuit as small as some transistors takes more time to finish that task. So that's the limiting factor. But if we can, and that's what we do when we make the transistors smaller and smaller, when you go from 180 micrometer to 3 nanometer these days, then it is becoming faster. Not only we can put more transistors in one chip, but also they become faster. So increasing frequency is one way of doing it. Another way is reducing the number of clock cycles. So let's say I have a video processing task that somehow needs 1,000 instructions, or let's say 1,000 clock cycles to finish the task. If I find a way to do the same task with 500 clock cycles, then I'm good, right? I'm improving the speed, and that's good. So what is limiting me again? In that case is something like instruction set architecture, right? If you oversimplify everything, if you want to run, let's say you have a processor that doesn't have a multiplier, you don't have a special multiplier designed for your processor. You have to use addition to do your multiplication. If your addition takes 1 clock cycle, you probably need like 30, 40 clock cycles to finish one multiplication. But if you spend some area on the chip, occupy some area on the chip, and design a multiplier that can finish a task in 1 clock cycle, which is possible these days. You can design clock cycle multipliers that are very fast. Then instead of having 40 clock cycles to do one multiplication, you can just use 1 clock cycle to do one multiplication. Here you don't increase the clock frequency, you just redesign your instruction set architecture. So every time I talk about instruction set architecture, I want you guys to have in mind that every instruction needs a hardware in the processor. So you can't just throw instructions in your instruction set architecture. You can, but you're making it look like a C language. It's not assembly language anymore. You can say, okay, we might as well put loops there, and every loops need 10 instructions. Or you have C for that. When it comes to assembly language, you usually want to have, they call basic instruction. You usually want to have basic instructions that they actually have an equivalent hardware for that instruction. So when you do shift, there's a part of the processor that is responsible for shifting. When you do multiplication, there's a part of the processor that is responsible for multiplication, right? So one research that we do in our lab is in-memory computing. In-memory computing does vector matrix multiplication. Okay, so if I want to, and what we do, we design the vector matrix multipliers. It's a pretty large system. Instead of having just one multiplier, you have a block that does the entire vector matrix multiplication. But then you add one instruction to the instruction set architecture, and you can say, do vector matrix multiplication. So now you can do vector matrix multiplication in 1 clock cycle because you have a hardware for it somewhere, right? So that's the whole goal. If you just keep creating new instructions in the instruction set architecture, you end up having something like a C language that is not even as nice as that. So the whole idea of assembly is we're going to have equivalent hardware for those instructions. We do have pseudo instructions that are a combination of 2 or more basic instructions. That's fine. We have instructions that to run this assembly, you need to run 3 other instructions, 3 basic instructions. They do it. I'm not saying that every instruction in assembly has an equivalent hardware. But what I'm saying is that the loop is, for example, something like a loop needs 10 instructions. We don't do that. We just, for example, we have branches. Branches might use 2 instructions. And by 2 instructions, it means it's going to activate 2 different parts, 2 different components in your CPU. So every time that you run an instruction, something is actually, some part of the hardware, some part of the chip is actually working. So if you design a multiplier, if your chip has enough space, so you can add more in-memory computing processors to it, then you can enhance your instruction set architecture, do something that would take thousands of clock cycles in 1 clock cycle. And the other thing is using parallelism. We're not going to talk about it because we do have a module on parallelism to increase the performance, but there's one to mention here because we did talk about it a little bit. So you just a reminder. So now, with this information, if I want to calculate the CPU execution time, I can use the number of clock cycles that I have for one program. Let's say somehow I have it, and multiply that by clock cycle time. How many clock cycles I need for each program, and how much it takes for 1 clock cycle. How long is 1 clock cycle? If I multiply these 2, I get the execution time. Clocks, multiply by period. Okay, now, this is a little bit more difficult, so this could be a question in the quiz. Let's say Facebook is using a bulk AES encryption task that needs 10 seconds on AMD FX1 processor that has 2 gigahertz clock cycle, clock frequency, sorry. And then we have the AMD FX2 processor that supports clock frequencies between 500 megahertz and 4.3 gigahertz. But it needs 20% more instructions to finish the same task. So what does it mean? It means that the instruction set architecture is different. So it needs 20% more instruction to do the same task. It's a different processor. It has a different instruction set architecture. So it needs 20% more instructions to finish the same exact task. But the frequency can be adjusted between 500 megahertz and 4.3 gigahertz. So now the question is, what value would you place into the clock multiplier register? In English, it means what should the clock frequency be, right? What should we have as clock frequency for FX2 processor to complete the same encryption task in 6 seconds? Yeah, it's a little bit complicated, but if you get the idea, so we want to execute the same task in 6 seconds. Right now, it takes 10 seconds to do the same thing. But the problem here is that we have two things that are changing from one processor to the next one. From FX1, going from FX1 to FX2, you have 20% more instruction, more clock cycles. You need 20% more clock cycles to execute the task. But your clock frequency can be tuned. So can you tell me what should the clock frequency be here? This is the last thing we're going to talk about in this class, so spend some time on it and try solving it, see if you can do it. So execution time is equal to number of clocks multiplied by clock period. That's the equation we get. This is enough to find the answer for this question. Okay, let's do this step by step. What is the first thing we have to find? Number of clock cycles. Right? Because we don't know what the number of clock cycles are. Okay, so before just putting the numbers here and making it complicated for yourself, let's see if we can move it around to see how we can calculate the number of clocks. The number of clocks can be equal to execution time divided by clock period. The worst marker ever. Clock period. Which is also equal to what? We have number of clocks based on this equation. We just move clock period here, and it's going to be equal to execution time divided by clock period.
So it's the execution time times the period, the frequency.
Absolutely. So we have the execution time multiplied by frequency, right? So we have both of these guys. We have the execution time of 10 seconds. That's 10 seconds. And the clock frequency is 2 gigahertz. So it means we have 20 gigacycles. Right? We have 20 gigacycles. Now we go to the next part of the question. Now we know how many instructions we need, how many clock cycles we need for this program. So what should I do in the next step? The next step, we can use the same equation to find the frequency.
Well, we need to add 20%, right?
Absolutely, yes. So the next step is, we have 20 gigaclocks here for processor FX1, but processor FX2 is going to need 20% more clock cycles. And it means that they have to multiply that by 1.2.
24.
So we're going to have 24 gigaclocks. For FX2, we have 24 gigaclocks. So we know the number of clocks. And what else do we know to answer the question? What is the information that's provided here? So we're in the second part, we know the number of clocks. Going back to this equation, we have this part. What else do we have? We have the execution time, which is what? 6, right? So we have this, if we do the math, we can find the clock period. Right? That's the answer. So we get the 20 gigaclocks, and I really suggest all of you to, if you don't already know the giga, kilo, mega, remember these things. You know, kilos per gigahertz is 10 to the 3, mega is 10 to the 6, giga is 10 to the 10, 9. But when it comes to bytes, it's 2 to the 10, 2 to the 20, 2 to the 30, right? So we have this number of clock cycles. As I said, we have to multiply it by 1.2. Now we get 24 gigaclocks. And then if we use the equation here again, we have 24 gigaclocks divided by 6 seconds. We're going to get 4 gigahertz. So 4 gigahertz is fortunately within this range. So we can actually adjust the clock frequency to 4 gigahertz for this kind of processing. Okay. So I'll try to design questions like this that you can see. You would be surprised how far you can go with this simple calculations. You know, we go to meetings that people ask about things that are not physically possible. It's not like you can't do it. But with simple math, because usually when they come to you and order something, and I'm saying, you would be surprised how many companies, how many managers come to you and ask for something that you can't do. And these simple calculations can fix the problem. And you go to a company and say, okay, I'll bring you a new processor, and let's see if you can do it in 5 nanoseconds, in 5 seconds. So what is the maximum frequency you can get? 4.3. You can't do it in 5 seconds. That's as simple as that. But if you accept the job, then you're gonna be the guy who fails in doing the job, not because you can't do it, because you didn't bring it up from day one and show them that this is not the way it works. I can never get this. As an example, I can give you something from our research. We work on a paper that actually ended up getting the best paper of the conference, and we had an improvement in memory computing part. We had 20,000 times improvement on part of the system. So we have a table that says we get 20,000 times improvement in performance if you use memory computing. But then we actually investigated how much of the computation can actually be moved to the in-memory computing. And that 20,000 time improvement changed to 10%. So it's not, so it was 20,000x. It means 2 million percent improvement changed to 10% improvement, because you can't really move the entire computation to that part. Still a lot of computation is happening in the CPU, which is not improved. So that's the Amdahl's law. So by knowing these basic things, Amdahl's law, this kind of quantitative analysis, as a computer scientist, or computer engineer, when you're tasked to do something, from day one you can see whether it's feasible or not. Right? So these are actually being used by myself on a daily basis, this kind of analysis. All right, we're good for today. We're gonna go, sorry.
So if you're looking for the clock multiplier, that means you want an answer of frequency?
If I actually, so you mean like when I said what should the clock multiplier be?
Right.
I usually don't ask the question this way because it's
Okay.
just too confusing.
Right.
Yeah, I just wanted to, I wanted it to be exposed to some terminology that is used in the community, but in the questions I don't want to confuse you. So I clearly say what should be the clock frequency. Yeah. Yep. Thank you.